Start the recording. Okay, so you want to go over JAL, and I assume like the encoding for it?
Yes.
Okay, so do you have the encoding up in front of you, like Appendix B in front of you?
No, let me go get it.
Yeah, so just fetch that, and then we'll talk about how to do JAL.
Okay, I have it now.
Okay, so what type of instruction is JAL?
It's a J-type.
Yeah, that's right. So we have JAL. That's J-type. And because of that, we can take a look at the J-type encoding and see exactly how we're going to do this. So if you'll notice for J-type, we actually only have 3 bit fields. So the bottom bit field is the easiest. It's just the opcode for jump and link, which for jump and link, it's looks like, is that right? 7 bits. Oh, I'm blind. Okay, yeah, I was misreading it. It's 110 and then 4 ones. And that's the opcode for JL. And the next bit field to the left of that is going to be your destination register. So in the case of jump and link, and then you write just a label, what's your destination register going to be? Because remember, that's a pseudo instruction.
Like in terms of like the offset?
So not the offset. So what I'm referring to is the following. So when you do jump and link, there's 2 parts. It jumps to this label, and it links or remembers where it's going to return to. And that's stored in a register. Which register holds that value, which it's going to return to?
Is it the program counter?
Nope, not the program counter. It's the return address register, the RA register.
Oh, the RA.
Because remember, at the end of every function call, you always have JRRA, right? So we can then say, all right, well, if we're just doing a regular JAL funct, which I assume that's what you're concerned with, not a JAL and then a register. But remember that this is indeed a pseudocode. The real instruction looks like this. It's going to be JAL followed by whatever register it is you're selecting, followed by a label. And in the case of the pseudocode, RD is just RA. So here, RD is going to be whatever the encoding is for RD. That's what the destination register is going to be in our encoding. But in the case of RA, if I recall correctly, I think that's like 1 or 2 in binary, but I need to check. Let's see. Does it say? I know it says somewhere. Just don't remember where. Yeah, there it is. So on page 3 of Appendix B, the very top left has all the register names and numbers. So RA is register 1, which literally corresponds to the binary encoding all zeros followed by a 1, because it's 5 bits. So in the case where you're doing the pseudo instruction, RD is always going to be all zeros then followed by a 1. But if we had a different register, if we were doing JAL and then some other register here, we'd change that to whatever that register encoding is. Sound good?
Yes.
Okay. So now for the last bit is the immediate, and that's kind of the difficult part. So, unlike how the immediate is encoded for branch statements where it's relative, do you remember how the jump statements are encoded?
You said it was like absolute, right?
Yeah, it's absolute, and I think you guys went over it in class. Do you remember how you're supposed to find that? Because in the immediate encoding, you'll notice that there aren't a full 32 bits like our address is allowed to be. In our encoding, we actually only have bits, 20 to 1? That looks right, 20 to 1. Yeah. So those are the only bits that we actually encode in our machine code. And the reason why we're not using the 0th bit is because since RISC-V is is not word. It's not word addressable. It's byte addressable. But the instructions are all 32 bits, and so when you write an instruction into memory, the addresses always go up by 4s, which we talked about previously. And because they always go up by 4s, the bottom 2 bits are always 0. So for any address where you have an instruction, the bottom 2 bits are always 0. Now that's not the whole truth, because there are extra extensions to RISC-V, particularly the C extension, which is for compressed instructions. So instead of needing a whole 32 bits to represent an instruction, you can do it in 16 for some instructions, in which case your addresses go up by 2s. So the bottom bit is always 0. Now that's a lot of extra information that you might not have talked about in class, but basically all I'm saying is that if you have 32-bit instructions or 16-bit instructions, no matter what, the bottom bit is always 0, so you don't need to encode that bit, which is why we only encode from 20 to 1 instead of from 20 to 0. But anyways, the point I was trying to make is that we're actually not able to encode the entire address. So why are we saying this is an absolute address if we're not even able to encode the entire address? How can I say with certainty that it's going to be absolute?
Does that have anything to do with like how we do our immediate encodings?
So it does. So here's what I'll tell you. So let me write down just some random address. Let's do A, B, C, D, 1, 2, 3, 4. So let's say that line is where my jump instruction occurs. So jump and link. And then let's say that my label is over here. Hex A, B, C, D. And then I'll do F, 0. You'll notice that both of these addresses end in 2 binary bits of 0. 4 is 1, 0, 0, and 0 is all zeros. So we have that these are word aligned correctly. And if this is where our label was, the way that we would turn this jump into an immediate is we would just look at the label and we would just take the bottom 21 bits, drop off the bottom 0th bit, and take the bottom 21 bits and encode it in this. So in this example, we would take a look at just these. And what we do is we would say, okay, I'm going to use all the bits from here. That's 4, 8, 12, 16, 20. And then you're going to take the bottom bit of this one, because we're encoding bits 20 to 1. Because this first one is 3 to 0. The next one is 7 to 4. The next one is going to be 11 to 8. And then 15 to 12. And then D is going to be 19 to 16. And then C is going to be 23 to 20. So I know it's a little scrunched up, but we go in increments of 4 starting at 0. So 0 to 3, 4 to 7, 8 to 11, 12 to 15, 16 to 19, 20 to 23. So we want all of these, except for the bottommost bit 0. We don't want that one. And we want just the bottommost bit of C, that 20th bit. And that is the number that we're going to put in for the immediate. So I'll write out what that's going to be in just a second in this case. But as a question to you, why is this an absolute address?
Mm.
I might not be able to hear you. Actually, I don't know if you did. You say something?
Oh no,
Okay.
I'm thinking as to why it is an absolute address.
So, for example, if we encoded ABCDFFF0, that would be an absolute address because it's the address that it's associated with, rather than the distance from two addresses. But what? Well, you might just not even know this, which is fine. You might not have been informed as to what happens with the rest of the top bits. But what happens is you take these bottom 21 bits, drop the 0th bit, and encode 20 to 1. And the top bits that you didn't encode, the topmost 11 bits that are left over, are actually used from the PC, the current PC address. So the interesting thing about jump instructions is that they're actually not able to take you from any program address to any other program address. And that's actually why I made these top 4 the same. Because if I had changed this to like B, for example, when I encode it, the bottom stuff is all going to be correct. But when I pull the top 11 bits from the jump location, from the current PC value, and I plug them in here, I'm not going to get to my correct destination. So when you're doing jumps that are really far away in terms of program memory, you can't just do it with one jump. You have to do it with 2 different instructions. The instruction is the AUIPC. I don't remember what the AUI stands for, but I do know that PC stands for program counter. And so when you run that instruction and then the jump, you're able to jump fully to any address within your program memory. But just jumps can only go so far. But they're still absolute because they encode the exact address rather than relative to where you're at currently. So any questions on that?
So you said that jumps are actually depending. It might need two
Yeah.
instructions of that. Okay.
Yeah, if it's too far away. So if we were going from here to here, this B does not get encoded in my jump instruction. And the way that you actually do the jump is you take the top 11 bits of your current PC value where the jump and link instruction is from, and you use those combined with the encoded bits to form your full address you're going to jump to. So it would end up jumping me to A, B, and then whatever this is, it'd be 8, 0, 0, 0, 0, not 8, that'd be C, plus whatever the encoded one is. And we want to go to BBC instead of ABC. So because of that, we'd end up jumping to the wrong location, which is why you need that extra instruction beforehand. Any questions on that?
We don't have to do that. Like,
No.
that's
I'm
right.
just
but-
I'm just
but
mentioning
that's-
this.
Okay.
So you don't have to worry about that. I'm just mentioning it so that you understand how it is that we can get away with only encoding the bottom bits. We can get away with it because we use the top bits from our current place in memory, from our current program counter value. However, if these are not the same bits, then we need to add in an extra instruction if we want to do long jumps. And it actually mentions that in the appendix. So if you go to the bottom for where the pseudo instructions are, and you go to, let's see, yeah, call label. So there's a call label function, and in that function, you can actually see the 2 instructions that I was referring to. It doesn't mention. Well, that's fine. Anyways, so in the call label pseudo instruction, you can see the AUIPC followed by the jump and link register, or JLR, pseudo instruction, which I was talking about earlier. But that's the only difference. And again, you're not going to really do that, so you don't have to worry about it.
Wait, I'm sorry. Where is call label?
It's at the very bottom of Appendix 4, on the last page, under pseudo instructions. It's just called, the instruction in the leftmost column is called call label.
Oh, yeah, the pseudo instruction. Oh, sorry, I was looking at the description.
No, you're good.
Thank you.
So the pseudo instruction is call label, and next to that you can see the AUI PC instruction, basically to do the top bits, and then you have the jump in link to do the bottom bits. Any other questions on that?
For the J-type, I see how it says that the 20th bit is going to be the most significant bit for the immediate,
Yep.
but then it's going to grab that from 10 through 1,
Yep.
place that there, and then... Okay, so, I mean, that's not too hard to understand. I was just making sure, yeah.
Yeah, so I'll go ahead and write out bits 20 to 1, and then we'd see how it gets spliced. So bits 20 to 1, remember that we're not including the bottommost bit. So if I was looking at this whole bit sequence of, I'll do it like this, hex, I'll give myself a little more space. So I'll do the whole bit sequence, hex, C, D, F, 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 0. So C is going to be 1, 1, 0, 0. That. D is going to be 1, 1, 0, 1. And then these are all a bunch of 1s, bunch of 1s, bunch of 1s, and then a bunch of 0s. So these are bits 3 to 0, 7 to 4, and then we have 11 to 8, 12 to 15. This is going to be 19 to 16, and then finally we have 23 to 20. So remember, we don't want the bottommost bit. We don't want to encode that one. And we're not taking all of these bits up here. We're just using bit 20. Sound good?
Yes.
So now what we do is we take all those bits and plug them in exactly where it says. So in the immediate encoding, it says first we're going to start with bit 20, which is this one. So in my immediate encoding, I'm going to say, okay, let's do that. Get rid of the stuff. So I'm going to first do bit 0, that's bit 20, and then I'm going to do bits 10 to 1, which is these 3, those 4, and then those bottom 3. That's these guys. So that's bits 10 to 1, not including this 11th bit here. So now I can write that out as 1, 1, 1, and then I have 1, 1, 1, 1, and then I have 0, 0, 0. And that's bits 10 to 1. And then the next swath of bits that I have is from, the next bit I have is 11, and then I have 19 to 12. So I'm going to do bit 11 here. So bit 11, that would be this guy here, which is a 1. And then finally I have bits 19 to 12. That's that last little section, which is just these 2 bytes. Or this byte. So we have 1, 1, 0, 1, followed by all 1s. There we go. And so this is what we would throw in the encoding. And if you were going to write it in hex, remember that the immediate is the topmost bits, so it is the topmost bits in the encoding, in this encoding. So you'd group them up like this in 4s. So this would be 7, F, this would be a 1, this would be D, and that would be F. So the immediate that you're going to encode is going to be 7, F, 1, D, F. So those should be the top 5 hexadecimal digits for your encoding. And the next 2 are going to be RD. So the next 2 spots are going to be whatever RD is, followed by whatever the opcode is. So again, in this example, we said that the opcode was this, and that the destination register was RA. So we do 0, 0, 0, 0, 1. And that's those bits there. But now when we encode it in hex, it's going to be hex 0, E, F. So we put in here 0, E, F. And that would be the full encoding for this exact layout. Any questions on that?
You said that for immediates, we go from the top, from like left to right.
I just did that because the immediate is in the encoding, the immediate is literally the leftmost field in that J-type encoding, right?
Hmm.
That's the reason why I said start from the left. Because when I'm converting this to hex, the actual full binary is going to be this followed by this. So it's going to be 1. So if I was to do the entire field, bit 20, bits 10 to 1, bit 11, bit 19 to 20, that's the entire immediate. And then that's followed by RD, which is followed by the opcode. And then if I group them in 4s, I can start from either the left or the right. It doesn't matter. I just said I'll start from the left. You'd get these hexadecimal digits. And then you have 0. You could also do it from the right-hand side over because it's a number of bits that's divisible by 4, so you're going to get the same either way.
Okay, thank you. I see what you did. Yeah.
Any other questions on that?
No. I think you answered a lot of questions I had for JLs. Thank you very much.
Good. You're very welcome.
Okay, so I mean that's most of what exercise 1 was about. Oh, so for exercise 2, we get a machine instruction. We first have to convert it to assembly verse 5, and then from there we then reverse engineer it to like a high level program like C, right?
Yep. So
And
it's going
then
backwards.
And then C is like just pseudocode, like just explain.
Not pseudocode, actual C code that you could run and get the same results.
Oh no, for part C.
Oh, explain in words what the program does. Oh, yeah, not even pseudocode. You're just explaining the idea. So if you went through it and like the two numbers, you took in A and B and you output C, and you take A times A, and then you do B times B, and then you add those two results, and then you store it in C. And then like you take the square root of C, you'd say, oh, this calculates distance, because it was A times A plus B times B, and then you took the square root, which is A squared, B squared, square root. So you just essentially interpret what the purpose of the function was, based off of what you can guess from the instructions.
Oh, I
And
see.
it shouldn't
Okay.
be that hard to guess what it is. It should be relatively simple.
Mm-hmm. So I guess this is so from adders to all the way to here. That's gonna be midterm because like I doubt we're gonna have homework for next week.
Yeah, your next homeworks aren't due until the 20th, I think.
Mhm.
I need to check though. But yeah, I believe it's the 20th is when your next homework is due, and you guys have your midterm coming up soon, right?
Yes.
When's your midterm? It's on next week.
Next Wednesday.
Wednesday.
Yeah, next Wednesday.
Okay. So that would mean 1 week from tomorrow.
Yes.
Okay. Did you have any other
I will-
questions for me?
I do, but I will be right back. I have to do something real quick. Sorry.
Okay, sounds good. So, what do you got for me?
Uh, Going back to homework 17, I was watching her video after how you explained how we should do branches.
Oh, yes. I was going to mention this to you. I forgot to mention it. The branching with respect to the address or the location right after is for a different assembly language for MIPS, which is very similar to RISC-V. You learn about MIPS probably in 300 if you take Dr. Regentova for it. But I was wrong when I told you have to do it with respect to the instruction right after. It's just the branch instruction. So you just subtract the two addresses of the branch and the label. Was that what you were going to say?
Yeah,
Yep.
'cause I watched her video and I was like,
Yes.
oh, okay, this is kind of different.
Yes.
But then, yeah,
Yeah, sorry
Thank
about
you.
that. I got
No,
that mixed up in my head.
there must be a lot. I mean, it makes sense. There's so much to
There
like
is a
remember.
lot to remember, yeah. There's a lot.
Um,
Did you have any other questions for me?
yes, I was looking back at homework 17, exercise 2,
Yep.
and then when they said write out the 5 to 21 bit immediate encoding, like that's just like the literal like immediate, and then we omit from 0 to 4, and from well, we just grab the from bits 5 to 21, and then what does it mean by if the immediate is extended, otherwise state that it is not extended, like sign extended, right?
Sign extended, yeah.
Okay.
Let me just double check or let me take a look at the homework. You said it was exercise 2?
Yes. Right, part C.
Let's see. Exercise 2, part C. Write out the 5 to 21 bit immediate encodings in binary. And that's for... of each instruction. Oh, let me look at the appendix. So we have an immediate, then you have a store. S-type. Store word is... let's see if I can find it. Okay, well, that's fine. So for example, for the SLL instruction, there's no immediate there, so we can disregard that. For the add I and SRLI instructions, I believe those are both I type, but I'm just going to double check. I know add I is. SLRI is... let's see if I can find it. Is also an immediate type. And then store word, I still haven't found... oh, there it is an S-type. Okay, cool. So I think what they mean when they say the 5 to 21 bit immediate encodings is you'll notice that for the I-type encodings, that's, what is that, 11 bits from 0 to 11. And then for the store word, that is S-type, and S-type is bits 11 to 5 and then 4 to 0. So I think it is a little weird why they say 5 to 21 bit immediate encodings, but I think they mean... oh, that's weird. Where's the 21 from? So I can see why they would say 5, because the immediate and the S-type encoding is broken up into two pieces. One that's bits 11 to 5 and one that's bits 4 to 0. And the bits 4 to 0, that's 5 bits. But I'm not sure why they have 21-bit immediate encodings. That might be a typo. But either way, it doesn't matter. You can just ignore that part, because all they're really asking you to do is write out the full immediate that would be encoded. So, for example, if you were to do it for, I don't know, the store word instruction where you're doing 16, you're encoding that in 12 bits of binary, and so you would encode it as zeros, 0001, and then 0000. This is that first hexadecimal digit, the second one, and the third. So it's hex, what was that, 010. And that's 16 in that's 16 in hexadecimal. This is 16 in binary. And so they're basically just asking you to write this out. And then when the calculations are done, if this is extended, you extend that value. And if it's not, then you do not extend it. And it looks like you want to, yeah, they're asking you to write it in binary, or they asked you to write it in binary. But that's essentially all they really want. And then you sign extend, if need be.
I see. Thank you.
Yep. Any other questions?
Yes. So for exercise 3 on homework 17, part B, it says in the answers that it cannot be encoded in a signed 13-bit. So that's the, like, if we were to get that on a test, that's how we would answer it, right? We would check if it's within the range of this assigned 13-bit number.
Yeah, because remember that for the BNE instruction, that is a B type, which, like you mentioned, has an immediate encoding, which consists of a total of 13 bits. And so you would calculate the offset that you're trying to get by. So the offset here in this case would be hex, what is that, 1040? And so this number has bit encodings. This is 3 to 0, 7 to 4. This is going to be 11 to 9, and this is bit 12. And I think that, let's see if I can find it. Yeah, and that exceeds the range because when you calculate the offset, and when it's computed in the processor, remember that the offset can be positive or negative. So this topmost bit represents the sign. So this would imply that we're jumping backwards because the topmost bit is a 1, and that's negative. So this is actually out of our range of encoding. This top bit would have had to be a 0, so we would have needed to encode it as hex. Well, it's going to look the same, hex 0400, but when we take the encoding, we need 2 bits for that topmost hexadecimal digit instead of just the 1. And that 0 is going to represent the fact that it's positive. And then the rest of it represents the magnitude of the number. And so yes, you're absolutely right. It's out of the range of the encoding. So the range of the encoding needs to go from positive, I'm trying to think what that would be in my head, 12, to the, no, not 12. Oh, that's right. Yeah. 2 to the 12 minus 1. That's your topmost bound, and then your bottommost bound is negative 2 to the 12. So that's the range of values that you can encode because it's 2's complement. And this number exceeds that range because if you were to look at this number, this is going to be 2 to the 12 plus some extra stuff plus hex 40, which is outside of the upper bound of this range. So yes, you're absolutely right in what you said earlier. calculate the range. If it's out of the range, it's an invalid instruction.
Is there no way for like maybe 2 jumps then?
So good question. So what if you needed to branch to that other location? Well, what you could do is you could branch to like an intermediary instruction, like to a different spot than where you wanted to go. And then at that spot, you write a jump instruction, and it'll jump you further. And
I
if
see.
that's not far enough, then you can do the AUI PC followed by your jump, which is can jump anywhere in the program. Any other questions for me?
Um, no, I think I'm good now. Thank you very much.
You're very welcome.
This isn't homework, but she was talking about it in class. What's the advanced standing form?
Oh, advanced standing, it's a form you need when you start to take more upper division classes in CPE and EE. So I can't remember exactly which classes you need it for, but pretty much most like 300 level classes you need advanced standing. And it's basically just a form which says I've made it through lots of the prerequisites, and I have, I've done, for example, CPE 200, EE 221, things like that. I don't know if those are some of the prerequisites, mind you. It's just advanced standing means you've taken a certain number of courses, and they're going to allow you to take higher level, junior level, and senior level classes.
Let's see. And then I need a permission or like the signature from one of the faculty members.
Yeah, so one of the faculty is automatically assigned to you as a faculty advisor, and they are the person that you would contact. If you want to find out who your faculty advisor is, I'd recommend getting in touch with your academic advisor, the person who you have to have meetings with every semester. I think it's Aline, right?
Yes.
Yeah, so just get in touch with her, email her about the advanced standing form, and she'll probably give you the form as well as let you know, or you can ask her, but she'll probably just let you know who your faculty advisor is. I believe it's assigned to you. I don't think you get to choose your faculty advisor. I may be wrong on that.
Okay, so I got the advanced standing form.
Yep.
And it says the courses are Math 181, Math 182, Physics 180, or 195, and then the labs for those, and CPE 100 and CS 135/lab.
That sounds about right, yeah.
Okay. And so do you need all of them in order to
Yes.
get into 300?
I'm
Okay.
pretty sure you need all of them.
The teacher did that. I'm pretty sure the teacher said something about how, like, you get like a waived, I think,
You
that
could get
you
it
can.
waived if you're missing one of those classes, but like you have everything else. You could probably like just ask for a waiver, and you can ask to get it waived so that, I don't know, you can take one class that requires advanced standing and be like, well, I have all the prerequisites for it, and even though I don't have advanced standing, I'm just one class off, and it's not a big deal because it doesn't have to do with what I'm going to be doing in this class, that kind of thing. So you can get it waived, but just in general, it's best to like get advanced standing as soon as possible. So take those classes if you're missing any.
Oh yes.
Are you cool if I erase the board?
Oh yes, thank you very much.
Yep. Any other questions for me?
I was taking a look, and I don't think I have any more questions. Thank you very much, Victor.
You're very welcome.
Have a great rest of your night.
You too.
Thank you. Bye bye.
See ya.